You? Okay. Let's see here. Okay. So today we're gonna discuss what are annuities. So before we get that, now an annuity is similar to our compound interest fund. So we're gonna kind of start there. Um, just kind of as a review here of what we did on Monday. All right. So on Monday, excuse me. Okay, so we did a compound interest, which was, I'll just write the formula here. So for our compound interest formula, so the amount of money after capital N represented years and some kind of an account, right? Some kind of savings account. And all right. So that was our formula here. And then let's kind of run through an example of how this would work, right? The way when you would use this would be over, as opposed to simple interest, is if you're in some kinds of savings account that compounds interest after a specific time, right? Whether that be monthly, quarterly, or even daily, right? So it's not the simple interest where at the end of typically 1 year, right, then the interest is compounded, right? Instead, what we take is the yearly interest rate, right, whatever that happens to be, and then break it up into smaller chunks that you earn throughout the year, right? And that's where the compound comes in, right? You earn interest, let's say it was monthly, after 1 month, and then the second month, that interest plus the principal gets compounded again, all right? So for example, let's say you start with an initial balance of, let's say, $12,000, right? And you have an interest rate that is 3.5%. All right, and let's say that K is 12, right? So just kind of an example, just choose some numbers here. So it's compounded monthly, okay? So here, I would like to know how much is in the account. And again, when we do these compound interest problems, we're under the assumption that I make one large deposit in the beginning, and then I just put it away and forget about it. All right, I don't put any additional deposits, and I don't take any additional money out. All right, so very idealized problem here, right? Not really true to form to how things normally work, but we'll actually touch on that a little after this example, all right? So let's say I want to know how much money is in the account, after 5 years. Okay. All right. All right. Okay, so we would like to find P of 5. Okay, so again, here there's no choice of formula. We just have one formula, but once we'll see later where it's going to become crucial that we pick the right formula. But for now, we have this here. It's just one, so I know I have to be that one there. So here we say, all right, so P0 is 12,000, right? That's our initial deposit. Right, then 1 plus R. Remember, always change R to a decimal. And then N was 5. It's 12. Okay. So we have it set up. We plugged everything in. We wrote it all out. And now let's plug this into our calculator, right? So here, yeah, bring up the calculator. Okay, so I have this ready to go here. All right, so I'll plug in 12,000. Open a set of parentheses, and then I'll plug it in exactly how I see that, right? 1 plus 0.035 divided by 12. Close my parentheses, then use this caret symbol here to get into the exponent. And then there I'll plug in 12 times 5, which is 60. So I'll just put in 60 there. All right, and then I'll hit enter. Okay, so then it looks like I have at the end of 5 years, $14,291. So let me go back here to my problem. We had 14,291 with 31 cents. Okay. All right, so then that's how we would run through a problem that involved compound interest. Okay. All right, let's see here. Can you clarify, Jorge, your question? What do you mean the amount of interest? I think usually the structure of this, though, usually okay, well, that's an example of a problem we did now. That's the one we just did, right? If they don't tell us the initial amount, then we just call it P0. And it won't be, again, if we don't know how much we start with, it'll be relative to our initial starting amount. Okay, so if they don't tell us how much we start with, then we just set P0 as some constant, right? And we would just, this would just be replaced by P0. And then I can calculate this number, and that'll be some number bigger than 1 that you multiply by P0. Okay, so so it'll be more symbolic. So you won't actually know an actually fixed amount. What you'll know is a percentage of the starting amount, right? So for example, if you just plugged in this in your calculator without the 12,000, and let me do that here. So let's see, that's 1 plus 0.035 divided by 12 raised to the 60th power, and then you get, so if you didn't know the initial amount and you don't know the ending amount either, the best you can do is this. Right, so you would have that much after 5 years, right? And the way you interpret that is that 1 is 100% of your initial amount, and you're gonna wind up with 19.1% more than you started with. And that's really all you can say if you don't know the ending amount and you don't know the beginning amount, if you don't have any dollar values. Okay, so clearly if you invested, if you started off with more money in this account, 19.1% is a larger number than if you started off with smaller. Yes, with what is given, right? And depending on what that is, right, then that kind of dictates what my solution would look like. Okay. All right. Any other questions? Okay. So now let's kind of dive a little deeper into this formula here. So it kind of help us guide what the next formula is, or how we arrive at the next formula. So if we look at our okay. All right, so this is kind of our formula. Now we want to say, all right, how did we arrive at this formula, right? Now, the way we arrive at this formula is really through what is called a form of recursion, right? Where if we think of, all right, let's kind of build this formula one step at a time, right? So here we wanna answer the question, how did I get here? Where does this formula come from? And it really comes from the simple interest formula, right? If you guys recall previously, it just has different names for the variables, but if you look at from yesterday, let's go back to A, it really comes from this formula here, right? Where we kind of adjust for the different compounding periods, right? But it really is just a variation on that one, all right? And I'll show you what I mean, right? So we start off with, we go to the bank, and P0 is just our initial deposit, right? Day one, we go in there, initial deposit. All right, and then I wait for the next compounding period, right? And again, here I'm going to keep it very general, right? It may be after a month, it may be after 3 months if it's quarterly, right? Or it may be the next day if it's a daily compound interest, right? So the next compounding period, I'll call P1, right? You're going to have your initial amount, P0, right, plus the interest that you earn over K times P0, right? The number of compounding periods, right? Because again, the rate is, if, for example, if it's 4%, it's not 4% every month, right? It's 4% divided up into those 12 months. So that's where the K comes in, right? Whatever those compounding periods are. Now, if we do some algebra here, we can factor out the P0. We get 1 over RK. All right, and kind of following this same idea here, let's say how much would you have in the next compounding period? Well, that would depend on the previous one times this same quantity, 1 plus R over K, right? Because now you're earning more interest, right? What you started with after that first month or whatever the compounding period is, added to it that interest. Now, if we back substitute, right, P1 is equal to this quantity. So we say, all right, that's P0 times 1 plus R over K times 1 plus R over K. And we get P0 plus R over K squared. All right, and then you can kind of see, all right, now you can kind of see, you can build from this in the nth compounding period. We get P the previous month times 1 plus R over K. All right, and then here, through some kind of a simplification, this turns out to be P0, 1 plus R over K to the M, and then you switch the M to whatever years times compounding period is. But that's where that formula comes from. Now, this formula works great, again, if it's the model where you take your money and one lump sum, and then you put it away, and you don't think about it, you don't think of withdrawing money, you don't think of putting any more money back in there. But really, this is not a typical way to save, right? Instead, what you might do is you might come up with a savings plan where you say, okay, I earn this much amount of money per whatever, per week, per month, right? And I'm gonna save X amount, all right? But I'm not gonna just put it under my mattress, right? I want it to actually do some work for me, right? So I put it away somewhere that it earns interest. So that cannot be solved with a compound interest formula, right? Because it doesn't say you deposit X amount every month, every week, every quarter, okay? So we need a different approach, right? This is not gonna work if we are describing where I have a set, I put away X amount each, whatever pay period. So that's where annuities come into place, right? So usually we don't, we save by depositing money on a regular basis. Okay, so let's kind of look at, well, how would this work if I try to kind of derive a formula like I did here? So instead, I don't have a P0. Instead, I'm going to define the variable to be D. And this is the D is going to refer to the recurring deposit. Okay. Excuse me. All right, so in our 0 month, the amount we have is simply D, right? Let's say it's $100, right? I go into the bank and I go, here's $100, start up a savings account, and then I'll be back the next period and deposit another $100, all right? So here we'll even simplify this problem where we'll just keep D to be exactly the same, all right? Okay, so from here, how much would I have after one compounding period? Well, it'll still be this quantity times the deposit. All right. All right. Or actually, excuse me, I should put the previous month. All right. But I have to go a step further, right? After that first compounding period, I'm going to put more money into the account. How much more? That much more, right? The value of whatever my recurring deposit is, right? So substituting here, kind of back substituting, we get 1 R over K D, right? Or if you factor out a D, K plus 1. Okay. And now let's say, all right, so that's after one compounding period. How would this look like after 2 compounding periods? So we would take the previous amount and then from there, right, I add in, so I'll calculate the interest and then I go back and I'm all right, here's my deposit for the next compounding period, right? However much that deposit would have to be, all right? Or whatever you decide on this being, right? Now, if I back substitute here, P1 is this quantity. And now you could start to see here that this, all right, 1 plus R over K times P1 is D, 1 plus R over K plus 1, and then plus the D out here. All right, and here we see, all right, now this is starting to this becomes D 1 plus R over K squared plus 1 plus R over K plus D. All right. This should have a, hold on, let me take a step back here. Okay, all right. Okay, so here, let's see, let's take a step back here. I jumped ahead of myself here. The P1 should get replaced by this. I forgot to set a parentheses there. Okay. No, I'm going to get to what. So this is just the process, the thinking of the equation, right? So I'm slowing down for you. Give me a second here. We're going to get to the result in a minute. Okay. Let's bear with me here. Okay. All right. So after the second compounding period, we have here. This will be D. And I'm going to factor out the D here, and we'll get 1 plus R this is D here. Factor out the D right here. Then we're left with 1 plus R over K squared plus 1 plus R over K to the first power, and then plus 1. Okay, if I kind of distribute that out and then factor out the D again. Now, as you can see, this starts to get, if I do this one more time, I'm going to start getting more and more terms, right? So this doesn't work out as nicely, at least right away, as my previous formula, right? So as it turns out, we have to do some kind of manipulation here to come up with something that is a little bit more or easier to work with. So I'm going to skip over some gory mathematical details here to arrive at a formula, right? So we do this recursion, and then we're like, well, wait a minute. If I manipulate it in this way, I can actually arrive at something that is going to be a lot more useful. All right, and that is the annuity formula, right? So through the process that I was doing above, we can arrive at this conclusion here, right? This is our annuity formula. All right, so it looks a bit more complicated than the compound interest formula. So we do have to be careful when we're doing this, that we use it correctly, that we input it into our calculator correctly. But let's kind of look at something like this, right? Now, when would you use the annuity formula? So they break down the variables here. Now, a lot of them, they're named the same as the compound interest formula, right? PN is the balance in the account after N years. Lighten that up here. All right, so that remains the same. Now, instead of P0, we have the variable D that represents the regular deposit. All right, and then R is the annual interest rate in decimal form as always. And K is the number of compounding periods in 1 year. All right, same as before, right? So all those variables, the only difference here is that there's no P0. There is a D that is recurring over and over again, right? One thing to, as a caveat here, if the compounding period is not explicitly stated, assume that there are the same number of compounds in a year as there are deposits made in a year. So what that means is, for example, if the problem states you deposit $100 per month. Okay, so that means that even though it doesn't, if that's the only thing it tells you, we're going to assume K is 12, that the compound of the interest rate is also going to be 12. Okay, so now when do we use this? You use this when, for again, right, a lot of this is going to come from being able to read through the problem and decipher that information, right? Look for those keywords, all right? So we're going to use this when there are regular deposits being made. right? As opposed to one lump sum like we did in the compound interest. All right, so if there are regular deposits being made, right, then we're going to use this annuity formula. All right, so let's work through an example here so we could see how to use this formula here. Okay, so in this example, it says a traditional individual retirement account, or IRA, is a special type of retirement account in which the money you invest is exempt from income taxes until you withdraw it, right? Caveat there, right? Not now, but at some point, they'll get their money. If you deposit $100 each month into an IRA earning 6% interest, how much will you have in the account after 20 years? Okay, so again, right, looking at this, we notice here, so at this point, we have two formulas to choose from, right? We have the compound interest and the annuity formula. Now, which one do I choose? So here, each month. So that's going to be our keyword, right? So here, what we want to take from that is that there is a recurring deposit. All right, there is a recurring deposit, all right? Excuse me. All right, so that means that if there's a recurring deposit, right, that I'm going to use the annuity formula. All right, let me write that up here so we can reference it here. So our annuity formula. One plus R over K, N times K, minus 1, and then all of that divided by R over K. Okay. So I have the formula there for reference. All right. And now we have to figure out what am I looking for and what information do I know? All right. It says, so now looking here at our kind of working through all of this, how much will you have in the account after 20 years? So what we're asking is this, right? Need to find. All right, that's kind of the last kind of sentence there is posing the question. All right, how much will you have in the account after 20 years? Okay, so I need to find that quantity there, right? So in other words, N, capital N, is equal to 20. Let's see if I know the other variables there. You deposit $100 each month. So our recurring deposit is $100. Excuse me. The interest rate, right? That one's easy. We see the percentage there. So the interest rate is 6%. All right. And then K. Now notice that here, it doesn't tell us how often this account is earning interest, but as a default, if we make a monthly deposit, we're gonna make the assumption that K is gonna be 12. If we made a quarterly deposit, then we'll assume K is 3, or excuse me, 4 since it's quarters. Okay, so however often the deposit occurs, we'll make the assumption that's how often you are earning some compound interest. Okay, and I think I have everything I need here, right? So looking at that, I think we have all that we need here to plug into my formula. All right. Okay, so now let's go ahead and hold on a second. All right. Sorry about that. Okay, so now let's go back up here to our formula and we'll say, all right, P of 20. Okay, and then here, D is 100. Then we have 1 plus the interest rate. And then up here, N times K, 20 times 12. And then minus 1. All over R over K. Okay. All right. So again, right, first step, write it down. So now how am I going to input this in my calculator? All right, so we're going to be careful here. So let me bring up the calculator here. Okay, so turn it on here. All right, and I'll plug this in exactly how I see it here. So we'll see, all right, we'll have 100. Open 2 set of parentheses here. And inside the first one, right, 1 plus 0.06 over 12. All right, raise that to an exponent here, 240, 20 times 12, 240. All right, now let me get out of the exponent by just hitting the right arrow, and then minus 1, and then close that second set of parentheses. All right, so far so good, and then hit divide, and then in my division, to make sure this works out properly, I'm going to open up another set of parentheses and put 0.06 divided by 12. Because I want to do that quantity first before I do the overall division. All right, and now we're good to go. Right? Here, let's go back here. All right, so D, our recurring deposit. Open up 2 sets of parentheses. The inside one. Well, the 2 brackets come from the formula. So we can just say that's the way the formula works. I kind of was going through the, well, there's 2 brackets in the numerator. I'm assuming Melody is what you're referring to. So here, if we look at it comes from the formula here now. I didn't go through all the details. I think we were kind of getting lost through me trying to derive this formula, but there are 2 brackets because the D is multiplied by this quantity and also by the minus 1. All right, so that's why we need 2 of it. Okay. All right, so let's go back here. Okay, and then here. Okay. All right, so everything looks good here. And hit enter. Okay. So saving 100. So saving for $100 a month after 20 years, you would arrive at the number you see there, and that is, let's go back here, $46,204. and 9 cents. Okay. All right. And now notice here by doing this, and again, this is over the course of 20 years. Now, if you just took $100 and put it away, let's say somewhere under your bed in a shoebox or wherever, so just to get an idea of how much more you would make by saving it in some kind of account that's earning interest, right? If we just kind of stashed it away somewhere, we had just had a bunch of $100 bills, right? 20 years at 12 months per year times $100 each month. If we do that operation, we get $24,000. All right, and then here this is no interest there. Okay. All right, so now you can see you are close to doubling it, right, over the course of 20 years, right? And again, if you would like this to be more money, then you just need to put more away. All right. Okay, any questions on this example here? Sure. Right. Again, these notes are available. There's a PDF copy, a blank one on Canvas. Okay. Any questions on the problem here? Okay, so how about, so now let's take a look here. So it says that you would like to retire with a savings of $1.5 million. And at the age of 24, you decide to invest in a 401k. All right. If the account has a 6.25% interest rate, how much would you have to deposit each month to achieve your goal by the time you retire at the age of 65? Okay. All right. So again, let's. This is a. So we're going to deposit each month. So again, we have to decide what formula we're going to be using. So we have a recurring deposit. Right, annuity formula again, right? If there's some kind of recurring deposit, we're going to use the annuity formula. All right, and let me write it up here so we can have as reference. All right. Okay, so now let's kind of decipher all this information here, right? Now now they tell us that we would like to retire with this much, right? So our ending amount, all right, should be $1.5 million. Okay. Okay, now, in how many years do we want this to happen, right? So here it says if we start at 24 to end at 65, so N is going to be the difference in those two numbers, right? So that's how many years we'll be contributing to this fund. So 65 minus 24. That is equal to 41. So in other words, P of 41 is equal to 1.5 million. All right, I see a percentage, so I know my R there is 0.0625. All right, each month, so K is 12. All right, and one thing I don't know, and what I would like to know, right, maybe a question I might, I want to ask ourselves, how much do I need to be putting away? So this is now my unknown, right? That is what I need to find. All right. So again, as you work through these, and what you'll notice, all of these questions in the section are going to have this similar tone, where either we'll be saving or we're trying to pay off some loan. Okay, and then we'll talk about those loan ones a little later here. But for now, we have this formula here, and we need to solve for D, right? Now notice that our formula is not where D is equal to, so we're going to need to do some work to get us there, right? But that's okay. Let's see here. So let's start off by just plugging in what we know. P of N right? So looking at this here, right? So P of 41 is 1.5 million equal to D, that is my unknown. And then 1 plus R over 12. All right, and then up here we have N times K, so 41 times 12 minus 1. And then over here we have R. Okay. Okay, so now we have our setup here. So now what we can do here is let me calculate all of these terms here, right? To make it as the simplest way to kind of go about this is, let me calculate the terms inside the parentheses here. So I'm going to switch over to my calculator here. And we have, so I'm going to plug in the parentheses there. We're going to have, so the parentheses, we had the inner parentheses 1 plus 0.0625 divided by 12. And I'm going to raise to that 41 times 12. All right, I'm going to get out oh, thank you. All right, and then, okay, so there we go, 0.0625 divided by 12. And I'm going to take away 1 and close my parentheses. They're already closed there. All right, thank you. Enter, and we get for just the inside the parentheses, we get this 11.8822. Now, when we go back to my notes, here it's there's no rule of how many decimal places to kind of round off at. To kind of minimize the amount of error, go at least 3, right? Just to make sure that our error is, we want to kind of minimize the amount of error that we get. So I'm going to go 3 places to the right of the decimal. So here we'll have 11.882. Let me go back here. So here we have 11.882. All right, and that D is still there, right? That didn't go anywhere, right? All right, and then we calculate that quantity in the bottom, 0.0625 divided by 12. And again, here I'm going to go 0.005. I'll go at least 3 decimal places. Again, if you would like to go on more, feel free to do that. Right, that will have a variation in our results, right? But it shouldn't be too major. All right, and then on this side is this value here. Okay. All right. So notice there's a little more work here, mainly because it's not, the formula isn't solved in the variable that we need. But from here, but after I get it here, it's just a little bit of algebra that we need to do, right? How do I solve for D? If I'm dividing by this number, first multiply by that number, right? Both sides of the equation. Oh, thank you. Okay. All right. So here, what we have is the 11.882 for my calculator, and then I just divided this part here. I put that in my calculator, 0.0625 divided by 12, and that's where the 0.005 came to. Again, right, I rounded, right? If you want to use 4 decimal places, feel free to do it. All right, but 3 should be good enough. All right, now it comes to, let me solve for D here so I can multiply both sides of the equation by 0.005. Again, that will cancel that out, and then multiply 1.5 million times 0.005. So if I do that, we get 7,500 equals to 11.882 V. All right. And then from here, we divide both sides. All right, so divided by 11.882. All right. And then we get D equals to $631. And 21 cents, right? So over the course of 41 years, right, if you start saving at the age of 24, $631, right, you'll have a $1.5 million at the end of that time period. All right. Okay. Any questions on that problem? I multiplied 1.5 million by 0.005. I'm solving for D, right? At this point, it just comes down to an algebra equation, right? Where we solving for X, essentially, the unknown. Oh, that should be a 0 there. That is our saving goal. Okay, We look at the problem. We want to retire with $1.5 million. If you want it to be more, you can say, well, what if I want 2 million? Then you could change it up. Oh, no, it should have been a 0. Yeah, it was a typo there. Mm, 1, 0. Let me double check my work. I think I might have put an extra 0 there. So 1, 5, 0. 1, 2, 3. No, I get 7,500. Try that again. Make sure. So 1,500, 3 zeros times 0.005. Right, that should be 7,500. Okay. All right. So doesn't seem too bad, right? 631, especially if by 24 you got a job with benefits, right? And then your employer puts on their end some part of towards your 401k. So it doesn't seem too bad. Again, right? Let's say you start at 24. Now let's say you didn't, right? Let's take a look at, well, what if I was unable to, and then I instead, let's look at the next example, right? So let's say my goal has not changed. I still want $1.5 million by the age I retire. But in this case, I started saving at age 35. So it's the same, exactly the same setup here as we have up here. The only difference is the N. I want to do this in less time. So I wait 11 years. Let's see what effect that has in what my initial deposit should be, or excuse me, my recurring deposit should be. So let me again rewrite the formula here. Okay, so all of the details remain the same. R was, so I don't keep scrolling back. R was 0.0625. K was 12. The only difference here is R. So I have N, I have R, I have K. The only difference here is N. I started at 35. So I'm going to give myself 30 years instead of 41 years. All right, and let's see how that affects how much I should start putting away. Okay, so, and again, P of 30 is going to be equal to $1.5 million. Okay, that is my goal, right? I set myself out the goal to that I want $1.5 million by the age I retire. Okay, so now we start off the same, plugging things in. All right, D is my unknown. 1 plus 0.0625 over K raised to the 30 times 12 minus 1 all over 0.0625 over 12. Okay, All right, so we've done this one already, so let's kind of run through it one more time. Same calculations, right? The number, really just the exponent is the only thing that changed up here. But let me let's bring our calculator back up here. Make sure it's on. And again, I'll start out by simply putting in the quantity that is in the exponent, right? Or excuse me, in the numerator of my fraction. So 1 plus 0.0625 divided by 12. And I'm going to raise that to 12 times 30 is 360. And then minus 1. Okay, so I get 5.489. Let's go back here. All right, and again, in the denominator, I'm going to go ahead and do that division, 0.0625 divided by 12, and that was 0.005. Okay. All right. So now from here, we have this. So let's see here. I'm going to solve for D, right? Once we're at this point, the question now becomes solve for D, right? So it's just kind of one of our equations. If I divide by 0.005, to get rid of it, you multiply, right? Both sides. So that leaves me 7,500 equals to 5.489 D. Okay. And then lastly here, if we're multiplying by that quantity, divide by it to simplify it to 1. All right, and then we get here, so 7,500 divided by 5.489. And there we get D to be equal to $1,366.37. All right. Now notice here, in waiting 11 years after, to start your savings, we have to earn twice as much for the remainder of the time to get to our desired amount of 1.5 million. All right, so now you can see kind of the effect of that compound interest, how that works if you don't start off. The longer the shorter amount of time that you have to earn that compound interest, the more you have to start putting away to begin with. Okay, any questions on this example here? All right, why don't we stop here for